So, for those of you who do not know or new to, my name is Ravi and my office is in the chemical engineering lab. For those of you who have not taken my thermodynamics course last semester, who are new to this department, right? So, basically the textbook and other things, references will be given in the sheet I'm going to give. But for now, if there is a book that would be very useful in the first few lectures, it is by Vectors, Tensors and the Equations of Fluid Mechanics by Harris. It's a Dover publication, available at a reasonable price for those of you who want to have it or expect to use it on a long term. Can go ahead and buy the book or some soft copies which we are making in the internet. Right? So this will be the book that will be following the first few lectures at least. And the basic book for problems and so on is the famous Word-Stewart line. Often I refer to as BSL, Word-Stewart line foot, transport. You don't need that right now. Word. As for the grading goes, it will be done along similar lines as it was done in the last semester, and I will just write it down. Everything will be there on the sheet. I am going to hand it over tomorrow. This one will have 20%. The rest of the 10%, right? Any guess on what? Attendance. Attendance, yeah. Okay. Many times I meet students after a long time, after I've taught them, and the only thing they remember is that I give a lot of importance to attendance. They don't remember whether I taught them transport phenomena. I mean, I even remember what is the first law of thermodynamics, but I remember that I gave a lot of importance to attendance. So attendance, I want to make that point, especially for those of you who did not take the thermodynamics or who have not taken any course under my instruction. The attendance is you have to come to the class on time. I saw many people coming a bit late, right? That you lose the attendance for that class, right? So invariably, you have to adjust the time. Obviously, this is certainly 3 minutes fast by as compared to my watch. There is silent went a few minutes early. You have to adjust it. I adjust it to the Google. I go to Google and type Indian Standard Time and periodically adjust my watch to that. Right? So right now it is roughly, so you can adjust your watches to that. Right? So you have to be here. I will invariably give 2 minutes grace time, after which you come, you will find the door is bolted from inside. So I want to take the attendance uniform for everyone. Some of you, it's not new to many of you. Particularly emphasizing this for those of you, especially from applied mechanics and mechanics and the new PhD students of chemical engineering who are taking this course. Right? Attendance will be given a lot of importance. If you fall short of the 85% attendance, then you will be reported and you are likely to get a W grade unless you are able to justify your absence to the academic section. Right? So attendance will be given a lot of importance, and if you attend all the classes, you will get 10 points without any questions asked. Right? And in my previous course, that is all some people got. So you get 10 marks for coming to the class on time. No questions will be asked. Right? So, of course, you can ask what happened, how many classes, and all that. I can give you if you want. It depends on how many classes we finally end up. It will be based on a certain percentage. 85% is less than that is W. If you attend 85% of the classes, you will likely get 0 out of 10. So there will be a range between 0 and 10 over which this mark will way, right? You have to be prepared for that. Yes, yeah. This is 10 minutes late. So let's now, are there any questions on this? So we'll continue, start with the main topic of the course, transport phenomena. Basically, all of you have taken some form of transport phenomena course. Basically, it deals with momentum. We can say energy and mass. Because when you consider momentum transport, it's basically, mass transfer, I can say. That's the way the name is given. This would typically correspond to, of course, in fluid mechanics. Energy, this would be basically come in heat transfer. And this is coming in mass transfer. And the three will be combined. Right? Any typical chemical engineering operation, all the three phenomena are bound to occur simultaneously. But for convenience, and also from a historical viewpoint, the fluid mechanics, where we don't consider any thermal effects, so mass transfer, I mean, even if a single fluid is flowing through a tube, there is mass being transferred. Typically, mass transfer is referred when you have more than one component. The number of components which I denote by capital C, more than one component, then you have certain effects typical of multi-component systems like diffusion and so on, which are not present in a single component fluid flow. So this division is both convenient. In simplicity, we want to consider first the momentum transfer, induce the mass transfer of a single component system. So all of this broadly can be considered as coming under continuum mechanics, or more appropriately continuum thermomechanics. That's the basic fundamental discipline under which what is usually taught as transport phenomena comes. You should be aware of that. So basically the important word here is mechanics. Right? In mechanics, there are two types of mechanics. Can someone tell me what? Can you think of two types of mechanics? Classical and quantum. That is one division. Right? So we are not going to consider quantum mechanics at all in this course. You think we cover will come under classical mechanics. Classical mechanics, can you think of further divisions in classical mechanics? Fluid mechanics, solid mechanics. There are many different aspects to classical mechanics. What I will, since I introduced the word continuum mechanics, which is something which is, you can call it discrete mechanics, or what is often referred to as mass point mechanics versus continuum mechanics. If we just talk of classical mechanics, there could be different answers for this question I'm going to ask. What would you regard as the most famous equation in all of mechanics? About particular mechanics, classical mechanics. Newton's law. There are many of Newton's law. Which one? Newton's second law is the most famous of which can be written broadly as F equals to ma. Right? F is the force. It's a vector. The underscore here refers to a vector. So the force experienced by a body is represented by vector F. mass of the body times the acceleration. Right? Now this equation as it is written is strictly applicable to only what we will call as the mass point mechanics, right? In which we assume the mass of the body is concentrated, or assumed to be concentrated. That's very important. At a point if you talk about the acceleration of the point that is moving in space, right? A projectile or even planetary motion was treated by Newton. They are assuming the planets are all mass points. There is a force acting on any of the bodies. Mass of the bodies are assumed to be concentrated at a point, right? That's now when you have a fluid flowing, this kind of an approximation will not help, right? So that is why we need another branch of mechanics called Continuum Mechanics. You cannot assume the mass to be concentrated at a single point. So each one of these three quantities that are here and the whole equation will undergo a change when you want to, for instance, describe. Let's just take the most common branch of continuum mechanics, that is the fluid mechanics, and the solid mechanics, elasticity, and so on, different branches. But you can only look under one branch called the continuum mechanics. So the fluid mechanics is the most relevant for chemical engineers, and that's what we will be covering for a large part of this course. Right? So the mass cannot be assumed to be concentrated. So here, the mass of the body is continuously distributed in space. We have to understand the whole concept of a body is really an idealized picture that is adopted in continuum mechanics, just as an idealized picture is adopted in mass point mechanics. So if they have a sphere, somebody hits a sphere, right, with a bat or something, it is going to move in space, right? So I consider that the whole as a good approximation. I consider that it's considered the center of the sphere. I'm just going to regard describe the motion of the sphere. I need to specify only. Let's say I fix a coordinate system, let's say x, y, z. So all I have to worry about is I'll assume the mass is focused at the center of the sphere. And I'll just trace the motion of the center of the sphere. So it's moving like that. So what is also important to understand, the relative motion between the elements, because after the sphere has a finite extent in space, there are many molecules and particles and so on that make up the sphere. It's not all at one point, right? So when you consider like this, you have no way of taking into account, right, any relative motion between the elements of the sphere, let us say. Right? But in continuum mechanics, this is very important. So how do we look at a body in continuum mechanics? Right? Suppose let's say I have a fluid flowing. Typically, fluid enters and it's flowing. Right? Because you can typically what you focus on what is called as a control volume. So you just focus because I'm interested only in what is happening within the tube. So I'm focusing my attention on this. But the fluid is constantly coming, undergoing various changes, and then moving out. Right? So there is a body in this. You can't really identify a body like the way you can identify a body in mass point mechanics. So the body, to understand this is very important, even though in solving the final equations, right, which we have to translate it to a control volume basis. But it's very important for you to understand this whole concept of a body, right, in continuum mechanics, and that will lead to what is called as a material description. continuum mechanics. So I'll just explain what are the properties associated with the body. Now I have to just consider a fluid flowing. I'm just going to consider a certain mass of fluid. I'm going to isolate this mass of fluid. And it could be in a tube or wherever fluid is flowing. I'm just considering a certain portion in space. Right? I'm isolating it. And I'm focused on freezing it that particular time. Right? So this has a certain mass at time t naught. Whatever the mass of fluid that is occupying this region in space, it has a certain mass. So just as in mass point mechanics, mass is effectively conserved in that I assign a particular mass to the body. So now I am saying basic proposition of continuum mechanics is that I can actually follow this collection of fluid which is there at time t, and at time some other time it's going to move and occupy some other position. Right? Because the fluid is moving, let's say. Right? So then the basic assumption of continuum mechanics is I can follow the body in space. Now how do I follow the body in space? Because here I need only one set of coordinates, maybe the center of the mass, to follow the body. Here, that approximation we have said is no longer valid because mass is continuously distributed. So here, now if I have to follow the body, I need to give an identity to the body. That identity is given in one of many ways, but I am going to consider the simplest way. So I will fix a certain coordinate system in space. Right? Now I take this body, let's forget about how it is moved at a particular other time. So I am focusing at x naught. So I am going to consider this as my body. That means I am going to follow this as it moves. Right? So, but the body, of course, is moving, but each point in the body is also moving to another location. So what I will see is with respect to a chosen coordinate system, right? I will consider the coordinate of each and every point in this space, which I have frozen at time t naught, right? So now there are infinite number of points in space, right? Infinite number of points are there in this space that I have made. Even into the smaller region, consider another body, even that will have an infinite number of points. So if you want to completely characterize the position of the body at a particular time, I need to specify the coordinates of all the points in the region of fluid which I am considering as the body of interest, right? So this is actually psi. These are known as the material coordinates. Here, and each point is called as a material point. It is not just a, it is of course mathematically it is a point, but it also contains some material, right? That is called a material point. So in continuum mechanics, the body itself is considered a collection of material points. Of fixed mass. If the mass is continuously distributed in space as opposed to being focused on a particular point, then you can easily argue that there is something called a density, a mass density, right, which can be defined, and that mass can be given by the integral of the density over the volume. body at a particular time. Now what happens when this body moves? So what we are seeing effectively is that suppose a point, so the basic assumption is I can actually follow the motion of each and every point in the body. But I take a particular reference time, right? Freeze a region of space that will have a certain mass of fluid. So this I am now saying this is going to be the body of interest to me. You know, the basic assumption of continuum mechanics, I can follow the motion of this body. I can actually predict the motion of this body. Right? That comes later, but first in this motion, I can follow the motion of the body. Now if I have to follow the motion from mass point, let us say the sphere has at certain time t naught. We want to simply describe the motion, not worry about how it is going to reach at another time. So at some other time, it would have reached some other position in space, right? And I need only one set of coordinates to fix that. The same idea holds if I want to describe the motion of the body, right? So this each point now gets mapped to a location, another location in space, right? And convenience, x1, x2, x3, x, y, z. That will make it convenient, and you are going to use vectors and so on to represent the position. So it is reached x, right? And we assume that in principle it is possible to find, right, the way each material point is going to move. So here, this is the basic description. If I can predict this, I can predict anything I want of the motion of the fluid. So basically what we want to do, predict in mechanics, and given the position of particle at a time t naught, we want to be able to predict how it is going to move based on certain initial conditions and the forces acting on it. So the same problem, I'm just stating the problem that we are interested in. The same problem transfers to continuum mechanics also. But now the body is a collection of material points. So if I want to describe the motion of the body, I should be able to describe the motion of each and every material point in the body. So I'm given the position of the material points at a certain reference configuration or a reference time t naught. Now I want to say how this body has moved at a different time t, or what is its location at a different time t. This is a collection of an infinite number of material points, right? I need to be able to tell how each and every material point, what will be its position at some other time t. If I can describe that, then I have described the motion of the body. Right? So it is much more complicated than mass point mechanics. Right? But these are the basic fundamental distinction is that the mass and the notion of the body itself is somewhat more, this is also an abstraction. We know that mass is not concentrated at one point of distributed. But for the purpose for which this was invented, Newton assumed the mass to be concentrated at a point. When you go to fluid mechanics, that assumption will not lead to anything useful. Right? So we have to now move to a different concept of the body itself, right? And what it means to predict the motion of the body. Are there any questions? So now we have looked at the first quantity, that is a mass, and along with it the motion of the body. That's one quantity we have seen how they are different. Right? Mass is simply, we just say this has a certain mass, whereas here we can only talk about the distribution or the density. Right? Here also mass is fixed, but to know the mass, right, we need to know the distribution of the density over the whole region in space. Right? So when the, for instance, let us say at some point this is rho of psi. So this is the density Now when it has reached the point X, it will have a different, this is a T actually. So there will be a different density distribution around that material point, right? So now the crucial point is, if I have, since I am assuming that the body has a fixed mass, and so this whole envelope has now moved into this, and we assume that all the material points that were enclosed in this has now moved here, enclosed by this boundary. This is the boundary at T. But since the mass is fixed, so if I integrate here, I'll get the same value. The value of mass is the same if I'm following the motion of the body, right? But the density distribution will be different, right? So this will be at T naught T, and this will be at T naught. And the density distribution can change. If we are focusing, of course, on a controlled volume, we know that the mass itself need not be conserved, and we can have accumulation of mass within the controlled volume. If we are following a body, the mass is conserved, the density distribution, everything else will change. Position will change, velocity distribution will change, everything will change. Right? So that is something that you have to understand. We focus on this. Now, what about the other two quantities, force and the acceleration? How will the law itself be modified? Because we cannot have simply F equal to ma. How is it to be applied for here, for motion of a continuum? Right? So this was not very clear. Even with Newton, it was problem was solved by Euler. What Euler said was you can use the same form as for mass point mechanics, but when you go to continuum mechanics, he suggested a simple looking but a profound change, and that is that instead of F equal to ma, this continuity, he said this would have to be df is equal to dm times a. Of course, of the whole body, there is a mass assigned to this whole body. No, you cannot assign a single acceleration to the body as a whole. This is very, very important to understand. There is no single acceleration to the body as a whole, because each and every point is going to be moving with a different velocity and is going to have a different acceleration. So there is no meaning to the acceleration of the body as a whole. Right? So this is how he changed it. He said that you can talk of a differential element of mass, you can assign an acceleration to it, and the Newton's second law would have to be modified as the differential force acting on this element is equal to the mass of the element times its acceleration. Right? But now so this is the way it is to be modified. Now there's another way of writing this equation for mass point mechanics. So I can write this as m dv by dt. Because acceleration is the time derivative of the velocity of the mass point, right? Then this can be written as d by dt of mv. So what is this d by dt of what quantity is it in the bracket? The momentum of the body. So that's why either you write the force as mass times acceleration or the time rate of change of the momentum. Right? When you go to continuum mechanics, this is almost trivial actually to write. Right? A is dv by dt, mass is fixed. So I'm taking the mass within the time derivative. So it's a very trivial modification. However, this has an implication in continuum mechanics. I'll just explain that briefly. We'll go through these in more detail as we get into the basic deriving the basic equation of continuum mechanics. This is just an introduction. Maybe if you don't follow all the steps, you don't have to worry too much. So now, if I were to write this, let's say now I'm looking at continuum mechanics. When I integrate this, it's a very formal operation, right? So what I will now write is this would be written as, I write this is dm dv by d, rather dv by d, the substantial derivative. Dm can be written as rho dv, right? And the whole thing can be written as d by dt of rho dv. This is what will be called as a substantial derivative. I haven't defined it as yet, but basically what you do is, if I want to calculate the total force acting on the body, right, then you can show that this is the time derivative, this is a substantial derivative that I'll explain that later. This is one that corresponds to the body as a whole, right? So I'm just doing some very hand waving type of operations here. So you can see that dm is written as really rho dv. That should not be a big problem for you. Differential mass is the density times the differential volume. So I'm just replacing the distribution. Not a strict proof. I'm just giving a plausible way of rewriting this equation. So rho dv, A I am going to replace by dv by dt just like here, but it has to have a different type of derivative because that is a substantial derivative. We'll explain that later, right? And then it is possible to show that the whole d by dt can be taken out. We'll prove all this rigorously later, and then I get something within the integral. So you can very clearly see, if you look at the units of this, the units of this is the momentum, right? This will be the momentum of the body as a whole. So even though you cannot talk of the acceleration of a body as a whole, you can talk of the momentum of the body as a whole. And how is this momentum calculated? Here it is simply mv, right? But here it cannot be mv, that will just be some average momentum, right? Because each and every material point has a different density, right? And also has a different velocity. So you have to take that and integrate it over the whole volume. Then you will get the momentum of the body as a whole. Whereas this operation is very trivial here. You just write A as d by dt and just take the m inside the derivative. Here it's slightly more tricky to do it. So what now you get is that the force, same of Newton's law, we have used both these forms. All it requires is a slight modification based on the constant of the body and the mass distribution and so on. So if I want to write F equal to ma, I have to use it in the differential form. If I want to write it as F equal to d by dt of mv, then I can write it in the integral form or apply to the body as a whole. So the vector, this is also force equal to time rate of change of the momentum of the body. So that's why you need d by dt. So we are focusing, because as I said, what is the meaning of that derivative and why we need a different derivative? Now, suppose let's say this is the region in space. I'm focusing at d naught. Right? Now I'm saying I'm going to consider this as my body. Right? Now, this has, I can calculate rho v dp for this body. Right? Because I'm freezing it at time t naught. Every point has a certain rho distribution. Every point I can assign a velocity. Right? So I can integrate it. It's all going to vary in space. So it's something that is varying. I have to integrate it over the whole volume, and I can calculate this. That's the momentum of the body. Because I'm focusing that, I'm seeing that as the body. So now if I say time rate of change of momentum of the body, right, then I have to consider the motion of the body. So it doesn't move, let us say, to t plus delta t. Right? So it has moved now, so I am going to have to move along with the body to calculate this new quantity of the momentum. Right? Because I am not fixed in space now, because that is the meaning of this. If on the other hand you had the other normal derivative, then what I am doing is I am focusing on this region in space, then I keep focusing on this region in space and see what happens at t plus delta. that is what I have to consider as a change. That is why it's very important. That is the control body rate of change of momentum. But if we want to consider the rate of change of momentum of the body, I have to move with the body. So I have not said that this is going to be the body of interest to me. So that's why you will see two types of time derivatives will come. We want to calculate the rate of change is that substantial derivative in terms of which the equations of continuum mechanics will have the same form as that of the mass point mechanics, and that's why it's very important to understand the material description properly, the concept of the body in continuum mechanics, right? Because the laws of mechanics are applied mainly only to the body, and then you can get all your control volume equations later, right? You cannot strictly, from a very fundamental viewpoint, we are interested only in, say, fluid flowing through a pipe, and my focus is on what is happening inside the pipe. You look at it from fundamental laws of mechanics, and especially if you want to motivate the laws of continuum mechanics from the mass point mechanics, then it's a substantial derivative, time derivative, that will come into play wherever the ordinary time derivative comes in mass point mechanics. Right? So that is the real meaning of the dy dt. When focusing on the region in space at t naught, and I just want to see what is happening, right? Then that is not equal to the force acting on the body, right? If I want to talk about what is the force acting on the body, then I have to follow obviously the body in motion and calculate its momentum as it is moving in space, and not say that I am just going to fix my attention on whatever it occupied at t naught and calculate the changes. That will not give you the force acting on the body, right? So this is how the equation of motion has to be modified, right? So the basic equations remain the same in form, right? But may not same in form, same in principle. Still you have the force. That is why this mechanics may be called Newtonian in character. It's not introducing any new, fundamentally new principle. Same notion of force equal to mass times acceleration of force equal to rate of change of momentum is preserved, but it is modified, right? To take it above all these modifications we have to consider when we want to consider the fluid in motion, where the assumption of conservation of mass is no longer valid, right? So now the third point is what is the details of the force itself is a very important point about the nature of the force that has to be taken into account when you are considering the motion of a fluid as opposed to simply the motion of a mass point, right? So typically in describing the planetary motion, which Newton had the greatest success, right? You could consider the gravitational force between two masses could be written, for instance, as G m1 m2 by r squared, easily, not the acceleration to gravity as we know, but the gravitational constant m1 m2 by the distance between the two bodies. Now this is something which is often referred to as an action at a distance. Even though the two bodies are not physically in contact, there is a force acting between them. Because even a body falling on Earth, right, falling down, right, to the surface of the Earth, is exposed down the acceleration due to gravity. That's also an action at a distance. Right? It's not actually physically in contact. Some force is acting that we can see, right, with the motion, and we say that this is caused by a force, right? So we can see something happening, and we postulate that there is a force acting on the body. This is what is called as action at a distance. Now, the continuum mechanics also, obviously, the fluid is flowing, it will also be acted by a gravity force, for instance, or any other forces like electromagnetic fields and so on. In continuum mechanics, it's important to distinguish then between two types of forces. Right? One is called as the body force. This is somewhat similar to the action at a distance that you have in mass point mechanics. That also has to be there. You cannot ignore that. But the most important force is contact force that comes because of, because for instance, if I am focusing on this body of fluid, let's say this would be a tube and this arbitrarily, isolating, right, the body, but of course the external forces are still acting, force due to gravity and so on, is happening on Earth. But however, we have all this fluid surrounding this, but in principle, there's nothing, it's a continuous fluid, is all I see. But in conception, I'm saying to apply the laws properly, as we have seen, we need to isolate like you do something called a free body diagram you might have done in certain branches of mechanics. Right? So you isolate a certain portion of the system, say what are the forces acting on the body. Right? So I have isolated this, but this is not just isolated in space, there's a whole bunch of fluid that is around this body. Right? So that is going to exert a force because of the fact that it is in contact with this body of fluid. That is what is called as the contact force. Right? This will lead to the concept of stress, as we will see shortly. So the nature of this contact force had to be discovered, and it was Cauchy in 1823 or so, who gave the most general description of this contact force, and that is why you can see Newton's mechanics, Newton's major work was published in around 1687, and if actually the equation of continuum mechanics is so obvious modification of mass point mechanics. First of all, Newton himself could have obtained, right? And he didn't obtain, and you can see more than 130 years were to pass before the nature of what we now call as the equation of motion, because this is an equation of motion, I think we MA. This is an equation of motion for continuum mechanics, but it is not complete because the force, there was one important force that we did not have to consider in mass point mechanics, which had to be considered here, and that is the contact force. Until that was properly clarified how to describe that, right, you cannot say that the equations of continuum mechanics have been fully and completely discovered. All the developments from here to here, right, were a process towards finding all of these, modifying all of this, the concept of the body, how the equation of motion should be modified, and finding how, what additional aspects we have to consider when you consider the nature of the force, and finally culminated a proper formulation of the contact force. So we will see what is the difference between the body force and the contact force, and how Cauchy's discovery, what is so significant about Cauchy's discovery that made the final resolution possible. Right? Are there any questions? If not, we continue tomorrow's class.